So question 1. So how do we figure out which one's the stronger acid? Well, we would have to look at the strength of the conjugate base, or the stability of the conjugate base. So if we look at this guy right here versus, let's do number 3, like that, between those two, if we go to the cardinal rule there, we see that the charge on all of them, actually, okay, the charge on all of those are on, they all have charges. The charges are all on oxygens. They all have resonance. And resonance and delocalization kind of go together. Now the induction now, what is the most electronegative atom here? We have fluorine. So it's going to pull the electron density on the oxygen towards the fluorine, which is a stabilizing effect. So because this right there is the most stable conjugate base amongst the 3, because as the most induction, then that means its acid form, which is that guy, is going to be the strongest acid. And then if we take a look at comparing these two, this guy right here has the chlorine closer to the negatively charged oxygen. Hence, it will stabilize it via induction better than this guy right there. So the strength of the acids, if we could rank them, that's the first or the strongest. That's the second strongest acid, and then that's the third. And so what would the answer be? Well, they want us to go from the weakest acid to the strongest acid. So this guy has to go first. And so that guy's off, that guy's out, that guy's out. So it's only between A and B. And we see that the next choice should be 3. So that leaves only answer A as the correct answer. Identify the proper curved arrows. So like I've taught you guys, when you see a prompt or a question, stop looking at the answers. Just do the question first. So can you draw the arrows from this resonance structure to this guy? What's happening? Well, we're taking a lone pair and we're bringing it. Well, let's zoom in so we can draw this a little bit better here. We're taking a lone pair and we're just bringing it between the carbon and the oxygen, just like that. So that would be the correct arrow. That's how we would do it. The formal charges, which those are correct formal charges. And so now I just go and look, do I have an answer choice that matches what I just drew? And so that one's out. Now between 3 and 5, paying attention to that arrow there, do you see how I'm bringing the lone, it's showing that the lone pair is going to the carbon versus in between the oxygen and the carbon. So my answer right here, the what I drew, matches that. So that would have to be A. Which of the following compounds is the most acidic? Well, when we take a look at this, the most acidic, we can scratch these out because they're bases. They have negative charges. This amine right here it's a very, very weak acid. because nitrogens or primary amines act as bases. Okay. We know their pKa's are around like 38, like just not acidic. So we've kind of really just eliminated the 3 right from the start. We have seen examples where the alpha carbon, the hydrogens that are attached to alpha carbons, or said another way, hydrogens, well, alpha carbons are the carbon one space away from the carbonyl carbon. And those hydrogens are acidic, but they have a pKa of around like 20-ish. But now this carboxylic acid right here, we know that carboxylic acids have a pKa approximately about 5. And so that would mean that number 2 would be the stronger acid, the most acidic. So B would be the correct answer. What happens if you didn't know the pKa's of 1 and 2? What would you do? Well, you would use you would take molecule 1 and turn it into its conjugate base versus the carboxylic acid, which is now carboxylate. And using the cardinal rule, you would go through and say, okay, C stands for charge. They both have a negative charge. Okay. A stands for atom. And we see oxygen has a negative charge, carbon has a negative charge. Which atom can stabilize a negative charge better? Clearly oxygen, because it's more electronegative, making that guy the strong or the more stable conjugate base, which would then make that guy the stronger acid. Okay. So when you don't know pKa's, cardinal rules it helps, and it's going to be the correct answer most of the time. There's going to be exceptions to that, but we'll worry about those when we come across them. Problem 4. Which of the following compounds contain an alkene functional group? Okay, that's just, do you remember your functional groups here? So this guy would be our amine. This one's our aldehyde. This is an alkane. This is an alkyne. This is our alkene. So that would be A. Which of the following bond line structures represent the same compound? Let's see here. How would we do this? How would we approach that? Well, we could like name it. That would be a good way to do it. So we have 1, 2, 3, 4, 5, 6. So that's the longest carbon chain. And so that is what? Hexane as the longest carbon chain. And we have a 3 isopropyl hexane. So that's the name for molecule 1. If we go to name this molecule 2, we see 1, 2, 3, 4, 5, 6. We get the same answer, 3 isopropyl hexane. So those two are the same. Okay, if you try to name this guy, number 3, you would see that it would be 1, 2, 3, 4, 5, 6. Nope, it would actually be, let's see, 1, 2, 3, 4, 5, 6, 7. Okay, so we would have what? A 3 dash or comma 5 dash dimethyl heptane. What about this molecule over here? 1, 2, 3, 4, 5, 6, 7. We could number it that way. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. How would we name that guy? 1, 2, 3. That would be a 4-ethyl heptane. So you can approach this problem by just naming them, and you can clearly see that these two are different names, and then those two are the same. So the answer would be 1 and 2, which is E. Now, what if you didn't know how to name molecules up to this point? Then it would require you guys just to see it visually. You could use the numbering scheme that I've just written there, and you just double check, is all the connectivity the exact same? And with doing that analysis, you'll also see that you'll come up with the same answer. So if you didn't know the IUPAC way of naming molecules, then this was just a visual inspection that to see if you could realize that they're the same exact molecule. Okay. Identify the resonance hybrid for the following compound. A little pixelated here. Well, let's draw the resonance. So in order to answer this question, we would have to draw the resonance, some of the resonance structures, wouldn't we? Okay, so what could we do? We have a lone pair there, on there. So we could bring that down, and then that there. So now we have a structure like this. And then we could draw another resonance structure, where we could take the negative charge here and go in between. Oxygen negative charge, boom, boom, just like that. So what do we have here? So we have negative charge, and if we number these carbons, 1, 2, 3, 4, we have a negative charge on carbon 1, we have a negative charge on carbon 3 over here, and we have a negative charge on the oxygen. So when I draw my resonance my resonance hybrid, I will draw all single bonds like that. There's my oxygen. And then I see that I have single bond character here and double bond character. See that? Single and double bond character. So I'm just going to put a dotted line that represents, hey, that's single bond character and double bond character. If I take a look at carbons 2 and 3, it's a double bond there, but a single bond there, and single bond there. So there's partial double bond character there. And so you can see the same thing between carbons 3 and 4. And then we can see, hey, the carbon-oxygen bond, double bond character, single bond character. So that's also like that. Now, we just go through and say, hey, carbon 1 had a negative charge on it. Carbon 3 has a negative charge on it, and oxygen has a negative charge on it. So those would be partial negatives, like that. Now, do we have anything that matches that structure? And so that's how you would approach the problem. And then you come in, and I know it's very pixelated, but there's the answer right there. Now, what it's showing you here, which is interesting, that this delta negative right there is smaller than that one. So it's showing you in the resonance hybrid that there's more negative charge over here than there would be on the carbons. So the correct answer would be 1, which is B. For the following reaction, identify the acid, base, conjugate acid, and conjugate base. So I'm not looking at these at all. Okay, so lithium is just a spectator ion, so we can just kind of ignore that it's there. Ignore that it's there. Okay, so that's negatively charged. That's positively charged. So negatively charged species are typically bases. But when I go from molecule 1 to that species right there, what has happened? There's 5 hydrogens, 6 hydrogens. So it's added a hydrogen. So by definition, molecule 1 has to be the base. And then molecule 2 would have to be the acid, because you can see from the acid to this molecule, it has lost a hydrogen. So that means this would be our conjugate base, and this would be our conjugate acid. And so that would be the correct answer. And now what would that be? What's the correct answer choice here? 1 is the base, so that's out, out, okay. 2 is the acid. That's out. So now it's only between B and E. So number 3 is the conjugate base, and 4 is conjugate acid. So that would leave that guy as the correct answer. Which of the following compounds have trigonal pyramidal geometry? So that requires just requires knowledge of how the valence or Versper theory on how the electron groups affects the geometry of the molecule. And so the correct answer would be that guy. So that one is trigonal planar. Trigonal pyramidal, sorry. Okay. We know water, that's a bent shape, so that's not it. Okay. The carbanion also has, that's that one there. And the boron species, that's trigonal planar. And hydronium, that one. 1, 2, and 4. Which of the following compounds are constitutional isomers? So in order to do that, what's the definition of a constitutional isomer? Same molecular formula, different connectivity. So that's probably what we should do very first, is look at the molecular formula of each compound. We could write that down real quick. So molecule 1, how many carbons does it have? 1, 2, 3. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. And how many oxygens? 2. Okay, molecule 2, how many carbons? 1, 2, 3. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. And, okay, same molecular formula. We have 3 carbons again. 1, 2, 3, 4, 5, 6, 7, and 1 chlorine. So that has a different chemical formula than the previous two. And this one, 3 carbons. 1, 2, 3, 4, 5, 6, 7. Okay. Wait, what did I miss? Let's see. Molecule 3, I see 1, 2, 3, 4, 5, 6, 7. It has a chlorine and an oxygen. Goodness. Totally missed that oxygen. And then molecule 4, there's no oxygen. There's 1, 2, 3, 4, 5, 6, 7, 1 chlorine. Okay. So just by doing the molecular formulas here, definitely 3 and 4 are not constitutional isomers because they have different chemical formulas. And those don't match the chemical formulas of molecules 1 and 2. So those are out. That's done. So do we have different connectivity? Well, look at that. We have an alcohol and an alcohol and an ether. Yeah, that's definitely different connectivity. So the answer is 1 and 2, which matches E. Which of the following structures have carbon with sp2 hybridization? Well, this carbon right here only has 3 groups, so that is sp2. This carbon right here has 4 electron groups, so that's sp3. This one's also sp3. And that has 2 groups right there. 1, 2, 3, so that's sp2. So the correct answer choice would be those guys, which is 1 and 4, which matches that. The carbon 2 and carbon 3 bond, so we're looking at this bond right there. And the following compounds results from the overlap of which orbitals? So for carbon 2, what's the hybridization state of carbon 2? sp2. And then for carbon 3, what is its hybridization state? sp3. So that sigma bond between carbon 2 and 3 is because you have an overlap between an sp2 and an sp3 hybridized orbital. Okay, so that would be sp2, sp3. And that matches. Okay, but it's good to say, hey, that goes to that one and that goes to that one. For the following acid-base reaction, identify the correct curved arrow mechanism. Well, sodium is a spectator ion. We don't need to worry about that. We clearly see that we have this thiol, and it's losing its proton, where the hydroxide is gaining a proton. So from that observation, we can see that the hydroxide is the base, and the thiol is the acid. So how would this work? Well, bases have to have lone pairs or some electrons. So if we zoom in here, it has 3 lone pairs there. We can take it, grab that proton, and stick it there. But how many electrons are on the sulfur? There's already 2. And then when we break this sulfur hydrogen bond, we're going to put the electrons on top of the sulfur, which means there's going to now be 3 lone pairs on that sulfur right there, and then the hydroxide turned into water. So that's the correct mechanism. I have not even looked at the answer choices. I don't do that. And we see if where that, so this one's wrong. That one's wrong because of that double-headed arrow right there. That's just, nope. Hydrogens never get drawn going somewhere. And so that one matches what I just drew up top. That one does not. So E. For the following reaction, identify the Lewis acid. Okay. So which species is gaining electrons? Look at it mechanistically. We have this coming in and attacking like that. Because now we have this chlorine that has a formal charge of +1. And then the iron atom right here has a -1 charge. So Lewis acids are species that accept electrons, and that's what the iron atom's doing right there. So that's the Lewis acid, the fluorine, which is molecule 1. The lone pair on the nitrogen atom in the following compound is... Can you draw a resonance structure for that lone pair on the nitrogen? If you can draw a resonance structure, then the lone pairs are delocalized. But if you cannot, then they are localized. Now, if I take that lone pair and put it in between there, is that valid? Well, it's a good question that you can answer by just drawing where you're moving that lone pair. So you would have that structure. But you have to be very careful. Did you violate any of the rules that you've been taught? How many hydrogens are on that carbon? There's 2. So there still has to be 2 hydrogens there because hydrogens don't move during resonance. And so when you zoom in real careful here, how many bonds does that carbon have? 5 bonds. Just formed a Texas carbon. So no, there's no resonance structure. So those lone pairs are localized. They can't move. So that's E. How many lone pairs of electrons are found on the indicated atom? Well, in order for that to have that charge there, what do we know? We know carbon has 4 valence electrons. My pen's dying. Let's see here. Let's see if we can get that to work. We know carbon has 4 valence electrons. 4 minus what equals a -1 charge? Well, we know that would have to be 5, right? So in order to have 5, what groups do we need on there? And the only way that would work is if we have 1 hydrogen and a lone pair. And so it only has 1 lone pair. So answer C. Okay, draw 3 resonance structures for molecule X. So this has lots of answers, lots of possibilities here. Okay, so let's just draw the molecule like this and draw some resonance structures. So what do we see? What patterns? We have a pi bond next to a pi bond. When you see that, we can have resonance structures like that. Okay. So we could have a double bond there, just like that. And so that would be two positive charges right next to each other. Would that be a good resonance structure, like a major contributor? No, because you have two positive charges right next to each other. But is it still, did we break any rules? No, that's still okay. What's another thing that I see here if I redraw the molecule? Let's see here. When you have a pi bond next to a carbocation, that's another sign of resonance. So that can come down like that. And so we could have a resonance structure that goes like this. And the positive charge would move there. That's valid. We could take this blue structure and work off of this one if we'd like. We know that we have a nitrogen here with a lone pair next to a double bond. That's a pattern that we've learned that can do some resonance. And so we could draw something like this. O minus. Plus charge is still there. Plus charge right there. So that's still valid. Could we have just gone from here and drawn a structure? Yeah, we know there's already two lone pairs there. So we could have drawn a resonance structure where this just goes there. So we still have the carbocation there, still the double bond there. And then we would have the O minus now, and then a plus charge right there. So for this problem, there's many answers that would have been acceptable. Many. Okay, draw the bond line structure for this molecule. That would be a carbon in the middle, and then 4 bonds right there. So that's not a true bond line structure. That's kind of a mix of condensed and bond line. So the true bond line answer would be that. You can see that this carbon right there is that one. And then we have 4 methyls. 1, 2, 3, 4. So if we expand it completely out, we could see a carbon to a CH3 to a CH3, CH3 to CH3. Now, this is a bond line, so that's also, so that would have to be a zigzag, would it not? Yeah. So what I would do is I see that there's 1, 2, 3 carbons in a row. So all you would do is go like this, draw our 3 carbons, and then let's highlight this one, would just be a wedge and a dash. So that's our bond line structure right there, showing the 3-dimensional shape of it. 1, 2, 3, 4, wait, yeah, just like that. So that is the most correct of the answers right there. Okay, calculate the formal charge on the atoms labeled. Okay, so if we do this quickly, a nitrogen with 4 bonds, so that's +1. We have an oxygen with 1 bond and 3 lone pairs, that's -1. So we'll just say negative charge. We have a carbon there. Okay. Let's do carbon 4 right here. So we do have a hydrogen coming off of there. Okay. So that would be just neutral. So that's neutral. Number 3. How many bonds are shown? We're not showing any. And so with that, there is 1 hydrogen coming off of there. And so there's 4 groups, so that would have a formal charge of 0. So molecule 1 is a +1. Number 2, -1. 3 is 0. And 4 is 0. Okay. And then it says indicate their hybridization state. sp3 for the nitrogen. Oxygen right there. For number 2, that is sp3 as well. And then carbon 3, that's sp3 and sp2. And is this, nope, 2 more. Okay, almost done. Okay, when we take a look at these structures, rank the least significant to the most significant. Well, the first rule states that the resonance structure with the least amount of formal charges, no, the first rule is the octet. So every atom there in molecule 3 has an octet. Carbon 2, or molecule 2, sorry, that carbon right there has a plus charge, so that means it does not have an octet. That's a negative, that does have an octet. And this plus charge on that nitrogen, there's still 80 electrons around it, so that has an octet. So molecule 1 has all octets. Every atom has an octet. And so from that analysis, just using rule number 1, we can say that the least significant would have to be molecule 2. Now to break the tie between 1 and 3, we go to the next rule and say, hey, the resonance structure with the least amount of formal charges is going to be the most significant. And so it would have to be that order. And then the last one, predict the position of equilibrium for the following reaction and explain your choice. So what's happening here? Can we identify our acids and bases? So that's negatively charged, and we see that it's going to this species right here. And so what has happened from there to there? We've added a proton. So that makes that the base. And then we can see from the alkyne to that, the alkanide, we have the acid. Conjugate base and conjugate acid, yes. Okay, so we figured that out. We know equilibrium is going to favor the weakest acid. So if we know our pKa's, then we could do that because we know that the pKa of this acid, the conjugate acid, is about 50. And the pKa of the acid on the left side is around 25. So based off of knowing that equilibrium favors the side of the weakest acid, we know it's going to go to the right. Now, if you did not know your pKa's, then you could also remember that equilibrium also favors the side that contains the weakest base. And so if we compare the stability of our bases, like this. And if we go through the cardinal rule, we can see that both bases have a charge. Both charged species have it on a carbon atom. But here's the cool thing here, is that, yes, they're both carbon, but they are different hybridization states. So this guy is sp3, this guy is sp. And so the sp carbon has more S character. And so more S character means that it's going to stabilize that negative charge better. This is also called effective electronegativity. So both are carbon atoms, but the sp hybridized carbon has more S character, so the electrons are closer to the nucleus because of the shape of the orbitals, and so it feels like the carbon is more electronegative, and that's due to the shape of the orbitals. And so because it's more electronegative, or the proper way of saying it is it has more effective electronegativity, it's going to stabilize that negative charge there better than this one. Okay, so if that's the more stable base, then that means that that is the weaker base. And so we found, hey, there's our weaker base, so equilibrium is going to favor to the right. And is that it? Yes, it is. Okay.